Hello, I welcome you all for this NPTEL lecture on earthquake resistant design of foundations. Today, we are going to talk about 38th lecture of this course. And this lecture is part of the last module of the course. That is the sixth module, which is on miscellaneous topics. So what we are going to talk today is foundations on slopes. And under the miscellaneous items, as we discussed in the last lecture, we are going to talk about two topics. One is rough foundation numerical examples, which we have covered in lecture 37. And today we are going to talk about shallow foundation on slopes, and we will continue that in the next lecture also. So when we talk about shallow foundation on slopes, these are the topics which we are going to cover. That is, first is its background, what is the reason for it, why we require, then static bearing capacity. Then we are going to talk about seismic bearing capacity, codal provisions, and finally some numerical examples. So today, in this first lecture on this topic, we are going to talk about background and static bearing capacity. And in the next lectures, the remaining three topics, that is seismic bearing capacity, codal provision, and numerical examples will be discussed. So let's talk what is the background here. So when I go on the background, it is like this. You know that in hilly areas, most of the construction is required to be done on the slopes. And because there is no flat ground, in that case, this requires that foundation need to be placed on slopes. And even in that case, even if you assume that the slope is stable, and when foundations are constructed on these stable slopes, still its bearing capacity is not the same as when you construct the same foundation on the flat ground. So this is very important issue, and that we are going to talk about that. And this is under miscellaneous. So this is an advanced topic, little bit. And this reduction which happens in bearing capacity is mostly on account of change in the values of dimensionless bearing capacity factors, which get reduced due to the slope as the slope angle increases. If slope angle is 0, then there is no change. Further, these factors reduces as seismic acceleration increases. So that last part, seismic acceleration, we will discuss in the next lecture. Today, we are going to talk that how the effect of slope is on the bearing capacity of foundation. Or I put it this way, that when the slope angle increases, what will happen to the bearing capacity of the foundation? How we can account that? And our discussion here, when we talk about foundations, will be only up to bearing capacity. We are not going to talk about settlement, because this is already an advanced topic. And what I'm going to talk today is taken from many of the research papers, which will be referred here and which will be duly acknowledged. So let's talk about that. First, when we talk about static bearing capacity, much work has been done by the earlier, and which is kind of a fundamental work which could be covered in this the lecture, rather than going in much in deep in the research work. So for example, the first work on the bearing capacity on slopes was done by Mehrhoff in 1957. Then Hansen and Weissig, they have carried out their work, the publication in 1970 and 75 have come. Then Saran, Sood and Handa, which is from India only, 1989, have presented something that how the effect of slope can be accounted when we determine the bearing capacity of the shallow foundation. Then some work done by Jemperline using the centrifuge test, 1988. So we are going to talk about that. And finally, Graham et al. Also given some charts to account for the effect of slopes on the bearing capacity of foundations. So let's discuss one by one. So while discussing, let me acknowledge that whatever I'm going to talk, that the material has been taken from these papers and the charts and all the things, and that is duly acknowledged that this is like what has been advances in the research. So let's see what has been done by Mehrhoff in 1957. So as published in 1950, this is long back, but still for the bearing capacity, because it is, as I mentioned, this part is not covered earlier, so that's why we are discussing another miscellaneous topics, being an advanced topic for this course on earthquake resistant design of foundations. What you could see on the slide, there are two figures. One figure on the left-hand side is showing where the foundation is on the face of the slope. Okay, that means it is not. It is passing through the slope itself. While on another case, foundation is not on the slope, but it is at some setback distance b, small b, away from the slope. But still, the bearing capacity of this foundation in the second case also get affected with the presence of this slope. So these two things we are going to discuss. So what Merhoff in 1957 proposed a theoretical solution to determine the ultimate bearing capacity of a shallow foundation. This is located on the face and top of the slope. So what you have in the first figure, what the first figure shows, nature of plastic zones under a rough continuous foundation on the face of slope. So what are the details here? Capital B is the width of the foundation. DF is the depth of foundation, which is normally, DF is measured from the ground level to the base of the footing. So you know the base of the footing, but ground level is not here. So what is done here? This will be measured from where this footing is intersecting at the slope at the down level. Okay, so that it is not from this point, rather this point where this footing is intersecting with the slope, and below this point, what is the depth of the base of the footing? That is the DF, that will be counted as the depth of the footing. Then under this, footing is subjected to what is called the surcharge QU. Okay, and this slope have make an angle beta with, this is making an angle beta with horizontal. So beta is the angle of inclination of the slope. QU is surcharge acting on the at the base of the slope. BDF. Now coming to here, if we have three zones as in the bearing capacity as usual, so this angle is 90 minus 5. That means this is 45 degree plus 5 by 2, and this is 45 degree plus 5 by 2. This is normally considered linear, right? And then this is log spiral. So normally, and this angle is, if you make an angle 90 minus 5, where it cuts at B, and then ultimately, if you extend this log spiral, this will join at point E. So this way we can have all the details here. In the second case, because the footing is on the not on the face of the slope, rather footing is on the top of the slope with width B, and you could see here again beta is the angle of slope, and you could see here height of the slope, which was not visible in earlier case. Then you have BF, which is from ground level to here 90 minus. So one additional parameter which is coming in addition to here in the first case, that is setback distance. That is, this is the this is basically top of the slope, and from here, what is this? If you have the distance to the footing is small b. So as naturally the in general one can expect that as the value of b increases, in that case, if you are going away from this point, when the value of b increases, in that case, the effect of slope will decrease. So there is called critical setback distances, which is given by some of the the researchers differently. So when the value of b increases, naturally the effect of slope will decrease. So after certain point, there is no effect of slope. So let's discuss. So both the situations, the Merhoff has given some charts, and before we discuss the charts, let's discuss that how the bearing capacity is determined by as presented by the Merhoff. The ultimate bearing capacity can be expressed by this expression, which is same as a Tarjagi's theory, as we discussed already. CNC plus QNQ plus half gamma B in gamma. And Q is here nothing but, as we discussed earlier also, that this Q can be find out. What is this Q? Q is simply, here you have Q is nothing but gamma df. There gamma is the unit weight of the soil, and df is the depth of the footing. So this is because once you fix the depth of footing, then this term will be also fixed. Then this relationship can be expressed in the following form. And when we talk about in the following form, then you need to understand that QU, NC and NQ, because the second term is split into two parts. Some effect is taken with the C, so represent NCQ, and most of the effect is come in N gamma Q. So the above equations, what has been done by Merhoff, that they have given only two coefficients, NCQ and N gamma Q, and that means the bearing capacity NQ has been eliminated. So the factor NC depends on NC and NQ, while N gamma Q depends on N gamma and N. Thus, instead of three factors, only two bearing capacity factors are used. And you know that these bearing capacity factors are dimensionless, there is no dimension. Now, coming to for purely cohesive soil, that is when phi equal to 0, then you know that this Q can be given by C and CQ because the second term will be 0. For purely cohesionless soil, that is when C equal to 0, so simply you can have Q equal to half gamma B and gamma Q. So for purely cohesive soil or purely, you require only one of these factors. Then Merhoff also defined the stability number NS, which is defined as gamma into H divided by C, where gamma is the unit weight of the soil, H, and C is the basically the cohesion. So if you have the large C value of cohesion, then the stability number will decrease. If you have small cohesion, then it will increase, or it could also increase with gamma and H. So let's see this in terms of C. So for example, for cohesionless soils, the stability number will be very high. So when H is height of slope, C cohesion and gamma unit weight of slope. So with this parameter NS, and having, let's say that now the issue is how this NCQ and gamma Q, which is used by Merhoff, is given by. So the charts here is give these values. These charts are for the case bearing capacity factor for a steel foundation when this foundation is on the face of slope. That is the first case which we have discussed. And in this case, you have two charts. The first chart is for bearing capacity NCQ, and another chart is for N gamma Q. Okay. So there are two charts, and on y-axis you have NCQ or N gamma Q. NCQ is varying from 0 to 8, while this N gamma Q is varying from 1 to 600. And one thing you need to notice that this for N gamma Q, this is in the logarithmic scale. While on x-axis in both cases you have inclination of slope, which is going from 0 to 90 degree in the first case, but in the second case, it is restricted up to 45 degree because beyond 45 degree will not be tenable for that once you have this, if you don't have a particularly cohesion in the soil. So anyway, so in the first case, when we talk about NCQ, there are two curves. One is d by b equal to 0, which is the solid line, while the second is dotted line, and this dotted line is the case when your depth of footing equal to width of footing. But for dotted line, there is only one line, one curve, which is when the slope stability factor NS equal to 0. So when one thing is here, let's consider for d by b equal to 1, that is the dotted line here only. You could see for this case, as the inclination of slope increases, bearing capacity factor NCQ decrease significantly. This was the case when d by b equal to 1. Again, another case when d by b equal to 0 is shown here in the solid line. So the result is similar, with the only difference is that this was curve, this is linear line. So that means what you could see, you have in both the cases, that means when the d by b is 1, then effect of slope is large compared to when d by b equal to 0. That means the value decreases very fastly of for the case when you are embedded footing. So as a result, your depth of footing is going to make a difference on the bearing capacity. Then once you have here, then what you have, we have here, when the stability number NS is increasing. In that case, when the stability number is increasing, what will happen here? That in the stability number, you could see for the same inclination of slope, the bearing capacity factor is decreasing. So this is the result, because we basically you could see that perhaps it could be the reason that when C is NS will increase when the C decreases, and when C decreases, then it is expected that the bearing capacity factor NCQ will also may have change also with that for different values of C. Now what you have here in the second case, when you want to calculate the value of N gamma Q, you don't have the effect of slope stability factor. However, you have the effect of angle of internal friction phi. And this first case, inclination of slope beta, this was the case when phi was greater than phi was 0. That means these curves are for cohesive sways. While in this case, when phi is greater than 0. So this is the case when phi equal to is greater than 0. And in this case, this is for angle of internal friction. So naturally, when you have the angle of internal friction is increasing, then bearing capacity factor is increasing for a given value of slope. Okay. And again, there are two cases. One is d by b equal to 0, which is the solid line, and d by b equal to 1. So that means when d by b equal to 1 is the solid line, dotted line, when d by b equal to 1, then it is expected that bearing capacity factor will increase because depth of footing is increasing. Okay. And the effect is shown here for 30 degree, where value of phi is 30 degree, 40 degree, and 45 degree. For three values, you have 6 curves here. So for each angle of internal friction, you have 2 curves. One is belonging d by b equal to 0 and d by b equal to 1. So what can be observed in these curves? That bearing capacity factor is decreasing with slope. These factors are also, as expected, decrease with the angle of internal friction phi. They also decrease when the depth of embedment get reduced. So this was as expected. But using this chart, you can determine bearing capacity factor NCQ and N gamma Q from, and once this is known, then you can use in your design. However, before that, you need to work out what is the inclination of slope, what is the value of d by b, what is the NS, all these things are required. Okay. Now, coming to the second case, when your slope, your footing is placed on the top of slope and at a set value distance b. In the same way, the first chart is giving you the value of NCQ with the distance of foundation from the edge of slope. That means the value of b. But this value of b is normalized with width of the footing b. B divided by b should be applicable for when the NS equal to 0. But when NS is greater than 0, then they have used b by h. H, where h is the height of the slope. Okay. So in this case, you have two normalization for NS equal to 0, b by b and b by h. It should be read for this axis. Now coming to the bearing capacity factors, there are these factors are for stability number NS equal to 0 to 4. Okay, and for each value, let's say for when stability number is 0, then you have two curves. One is solid line, which is for d by b equal to 0. Another is dotted line, which is d by b equal to 1. Within these two solid lines, these have been drawn for slope angle starting 0, 30 degree, 60 degree, 90 degree. Okay, so this dotted line you could see 1, 0 degree, 30 degree, 60 degree. This will require 60 degree, and this will be kind of 90 degree. So these different curves are there. Then similarly, you have this was the inclination of slope. So according to, you can select the whatever the inclination of slopes, and then bearing capacity factors can be determined from. Now coming to the second part, that is N gamma Q. Again, y-axis you can see is on the log scale, while distance of foundation from edge of slope has been put in terms of ratio, that is b by b, and you have here inclination of slope beta, angle of internal friction phi. So all these you have 0, 30 degree, this 20, 40. So these, what is this? This you have 30 degree and 40 degree is angle of internal friction. While inclination of slope is given here, that is 0 degree, 20 degree. So naturally, when the angle of internal friction increases, the factor n gamma q will increase. However, when the inclination slope, that is beta, increases, then it is expected that bearing capacity this factor will decrease. So this is it. So this way we can determine the value of the bearing capacity factors using these charts, and we will discuss one numerical examples on this. Now coming to the second theory of that is proposed by Hansen and Lessig. Hansen worked on this in 1970, proposed a following relationship for the ultimate bearing capacity of a continuous foundation at the edge of the slope. And what is the equation? QU equal to CNC lambda C beta plus QNQ lambda Q beta plus half gamma BN gamma lambda gamma beta. So there is only a small difference in this equation. In the last equation we have discussed that Hansen and Lessig have introduced three more parameters, lambda C beta, lambda Q beta, lambda gamma beta, to take care of the effect of slope. Earlier what we have done? We have reduced the bearing capacity factor NC, NQ, and N gamma. Basically, we matter of a club, NQ was eliminated, and then we whatever the new factor have come. So on those new factors, there were charts that according to your slope, you can determine the NCQ and N gamma. Here we have separate out those factors. So here lambda C beta, lambda Q beta, and lambda gamma beta are called slope factors. And for example, lambda C beta will be given by this relation NQ lambda Q beta minus 1 divided by NQ minus 1, where NQ itself is nothing but NQ is the dimensionless number. And for phi greater than 0, if phi equal to 0, in that case lambda C beta can be directly defined 1 minus pi beta pi by plus. And here beta is nothing but the slope of the angle of the slope, which is, so if you are representing pi in radian, then it should be in terms of radian. So then lambda Q beta equal to lambda gamma beta. If we substitute this number, then what you will have that both are lambda C beta is given from this relation, while lambda Q beta lambda gamma beta is given from this relation 1 minus 10 beta square for beta greater than less than 45 degree. And if it is greater than 45 degree, then we have a different treatment. Here, let's work on this even for less than 45 degree. If I have beta equal to 45 degree, then tan 45 will be 1, and in that case, at 45 degree, lambda Q beta and lambda gamma beta will be simply 0. Then what you have, once you have this value 0, and you substitute in the equation, the equation 2a, then you left only with the first term. Q in these terms is gamma df, as we discussed earlier. Okay. Now continue with that. We have talked about how to determine lambda C beta and lambda Q beta. That is known to us, lambda gamma beta. But how to determine the value of n gamma, which is coming in the equation, is not discussed. So we need to find the value of n gamma and then about n gamma is given for phi equal to 0 condition. That means when you don't have that means for cohesive soils, basic pointed out that with the absence of weight due to the slope, the bearing capacity factor n gamma has a negative value and can be given as. So n gamma is minus twice into sine beta, where beta is again the angle, the inclination of the slope. So that means they have linked, basic have linked the value of n gamma with the slope angle. So once you determine the value of n gamma from this, then the NC in simply 5.14 and NQ equal to 1. So using NC equal to 5.14, NQ equal to 1, and n gamma which is given from the above equations, and then substitute the other numbers. So what you have is Q equal to CNC. NC has been put as 5.14 multiplied by whatever you have this here. So NC should be multiplied by this factor, which is given here, lambda C beta 1 minus twice beta pi plus. So what you have here, 1 minus twice beta, this pi plus 2 will be simply 5.1. Okay, so this is the case CNC Then you have Q gamma df, Q into, you have then Q into, you have Q into NQ into lambda Q. So you have NQ and NQ, lambda Q beta is given here, 1 minus beta square, and Q is gamma df. Gamma df 1 minus 10 beta square is there, all right, and this is NQ is also 4. Because NQ value has been substituted here from NQ value has been substituted from here. What is NQ here? 104. N gamma is minus by sine beta gamma df. All right. So you have Q equal to gamma df as mentioned earlier, and lambda Q beta is put lambda Q beta equal to 1 minus 10 beta square in beta 10 beta square. So yeah, NQ has been put 1. Yeah, NQ value is put here 1. NC is 5.14, and yeah, it is given here. So for 5 equal to 0 condition, NC is 5.14, NQ is equal to 1, and therefore this equation 2a will takes the following form. This equation will becomes NC you have substituted 1 minus pi beta 5.14, and NQ has been substituted here, and in meanwhile you have Q gamma df and NQ is 1. Then finally, that N gamma is substituted by sine beta, and then you end up here in this equation. So finally, for Hansen and Wesley have proposed that QU, that is ultimate bearing capacity, can be determined from this relation. So you have a coefficient of C, you have a coefficient of gamma df, and then finally gamma B here. So all these coefficients depends only on beta, that is the inclination of slope. So this was the proposal by Hansen and Wesley, and you could see due to the presence of the slope, this value get decreased. For example, if you have beta equal to 45 degree, you can have 2 into 45 degree means 90. 90 can be written as pi by 2, and pi by 2 is nothing but pi by 2 is 1.57. So this can be decreased and can work out. And the same thing is here, because beta is known, so 10 beta is also known. And for further equations. So this was about Hansen and Wesley. Then further limit equilibrium analysis and limit equilibrium and this solutions have been carried out. And what has been carried out? This was done by Saran, Sood, and Hanna in 1989 at University of Roorkee, and they have provided a solution to determine the ultimate bearing capacity of shallow continuous foundations on the slope, top of the slope, using the limit equilibrium and limit analysis approach. And according to this theory, for a strict foundation, again this equation determines the ultimate bearing capacity, and this equation is same as we discussed in the Tertiary theory, where NC, NQ, and N gamma are the bearing and numerical values are given in the table. So these NC, NQ, and N gamma are bearing capacity factors, and let's see how these bearing capacity factors get changed or affected when you have this presence of slope. So here, the first table is telling you that this bearing capacity factors, this is based on Saran, Seed, and Handa's analysis of 1988. What you have, this is in this table, only factor NC has been given, which is for different values of beta, ranging from 10 degree, 20, 30, 40, 50 degree, and df by b equal to, initially it was 0, then it has been considered, which is 0 to run. So then you have this here, df by b equal to 1 and 1. So when df by b equal to 1, you can use this, and then you need to see the setback distance. Setback distance is also, if you have the case, then your depth factor is also 1 and setback distance is also 1. In that case, you can find the bearing capacity from this column, this row, and accordingly, whatever, that you have factor NC, according to factor NC, according to this beta degrees angle, you can determine this what is called soil friction angle phi, which is in degrees. Which is here, so you have 40, 35. What is this? These numbers are friction angle, which is in phi. So ranging from 30 to 40 degree. This way, you can find the value of NC from this table. So in this case, this table is basically telling, because always you know that NC will be a function of phi in any case. But here the effect of beta, that is the slope angle, from in the range between 10 to 50 is taken care on NC, as well as df by b equal to, it could be 0 or it could be 1. Suppose if your df by b or b by b either 0 or 1, if they are lying in between, then you can still use this table by using the interpolation. And this was the story for NC. For other two parameters, for NQ and N gamma, this is given here. For NQ, what you will see, the range of the slope is not wide, because the one condition here is required that the value of beta can't be more the friction angle phi. So that condition need to be satisfied whenever you use this. Then for different values of beta, 10, 20, 30 degree, you can pick up one value of beta, and then soil friction angle phi is ranging from 10 to 40 degree. So accordingly, whatever the angle of internal friction is known to you, select that angle, and let's say for 30 degree angle, then using 30 degree beta, then you get the value here 8.98. Then similarly for 20 degree, you get more. As you decrease the slope, then this bearing capacity factor will increase. This is happening here. So this was for NQ. Similarly for N gamma also you have, but for N gamma you have more data compared to NQ. So these tables have different range of the data, and that was at the time the research carried by Sarang, Seed and Handa. So whatever their experimental work, and so that has been presented here. So this was the case. Now continue with that. There are others also, as we discussed, that Jumperline in 1988 reported the results of 215 centrifuge tests on continuous foundations located at the top of the slope of cohesionless sand. And based on these 250 tests, Jumperline proposed that the ultimate bearing capacity of the continuous foundation can be expressed as Q equal to half gamma V N gamma. Here, one thing is important to understand, that while this equation looks very simple for ultimate bearing capacity, but it is assumed here that C is 0. That means this is applicable only for sandy slope. And what the Jumperline proposed, that was based on their results of 215 centrifuge sand test. And this is, as mentioned, it is for cohesionless sand. So the equation proposed based on 215 tests is this. Now we need to see what is the effect of slope on this factor N gamma 2, because there is only one factor. First of all, this theory is applicable for cohesionless soils. That means sand only. That is one thing. Second thing, that this is ultimate bearing capacity is given from this relation. But in this relation, how the value of N gamma Q get changed with the slope. So that is given here. What have the extending the work of Jumperline in 1988, Shields in 1990, normalize the N gamma Q values proposed by Jumperline in the following formula. So what is there? If you divide by this, N gamma Q R. So on the right hand side, you have this equation, though it appears very long equation. But let's see, if I don't have any slope, then beta will be simply 0. And in this case, tan 0 is 0. So you can still, once you put beta equal to 0, it must simplify. This factor will go, only one will be left out. And here in the second factor, again, it will be, this ratio will be 1 for tan beta equal to 0. And once tan beta equal to 0, this factor will be also gone. So you will left again 2 by 2, that is 1. And this way, this equation is very much simplified when beta equal to 0. And when beta equal to 0, this is non-dimensional, and this will become when beta equal to 0, this term will automatically be 0. So this equation is much simplified when you use for that beta equal to 0 means there is no slope. Now, n gamma q r in this equation is the value of n gamma q for a reference continuous foundation at the surface of level ground. That is when df by equal to 0 and b by b is infinity. So for these two conditions, when the surface and the df by b equal to 0 and b by is infinity, in that case, then n gamma q r is a reference number basically, and that number is dimensionless bearing capacity factor. The magnitude of n gamma q r can be given by the following relationship. It can be found out 10 to the power 0.1159 to 5 and minus 2, and then same thing is here 10 minus 0.34 minus 0.2 log. Here one need to understand that in this equation pi is in degrees, not in radian, and b given is in inches. So b is not in centimeter in this equation, b is in inches. So what we do? We find the value of for given situation, for given value of phi and given value of b, you can determine the value of n gamma q r. Once you determine the value of n gamma q r, then using equation 1a, you can find the value of n gamma. And once n gamma q is known, then you can determine the ultimate bearing capacity from this equation. So this was about what is the Gamper line and then lateral shields from centrifugal test. Now continue with that. Graham et al. Did some theoretical analysis and presented the value of n gamma q and how the effect of depth is on these numbers. So let's see that Graham et al. In 1988 provided a solution for the bearing capacity factor for a cell of continuous foundation on the top of the slope in granular soil based on the method of stress characteristics. Okay. The failure zones in the granular soil for embedment, that is df by b, and setbacks b by b assumed for this analysis are shown here. So what you have here, first of all the failure zones, and this is for d embedment d by b and setback distance as b by b, which has been assumed for this analysis. Let's see here. In this figure, first figure, what in both figures you have n gamma q, and both figures are for df by b equal to 0. In this case, b by b equal to 0 is, you have this these curves belong to this b by b. Then capital B by b in this case has been, this is for different value of phi, 30 degree, 35 degree. So b by b equal to 0.5 is for this dotted line, and b by b equal to 0 for other lines. So as the value of b is increasing, so you could see that when the value of b increases, then at the same time this bearing capacity factor also increases. So these curves are for different value of phi. One can see that as the value of phi increases, if I see here 40 degrees is the maximum here. So when this is increasing, then this factor is increasing. Otherwise, when this is decreasing, then this factor is also decreasing. So this was the case when you have beta, you know that this your b by b equal to 0 surface putting and embedment with small embedment b by equal to 0.5. But if you have the further large embedment, this here the setback distance is increased. Let's see further. So here setback distance has been already defined in the let's go through this figure where the setback distance has been defined in the first figure. Yeah, you could see in this first figure, b divided by b will give the ratio, but this ratio will be also increasing when you increase the setback distance. So effect of setback distance is also shown in this figure, and that effect in this table. Yeah. So if the effect of setback distance is simply saying that for the same value of phi, when setback distance is higher, like for example b by equal to 0.5 instead of 0, then for the same value of beta, this increase can see in the one. Same thing is here, that you could see that what is this b by b equal to 1, solid line and dotted line. So dotted line, first of all, is above the solid line for the same value of phi which was expected. And you could see in these curves that the effect of like basically setback distance this way, because it is 1 and 2. So when it is 2, it increases, and at the same time you see the effect of beta, that is slope angle, on these values. Continue with that. Graham earlier chart was for df by b equal to 0. Then the same chart has been repeated for df by b equal to 1, and these are very wide, very clear. So one can see that first of all, when the effect of the damping this beta, which is your basically slope angle, is increasing, in that case the value of this factor n gamma q will continuously decrease, irrespective of the type, irrespective of the angle of internal friction. So it will decrease. Then you have the difference between setback distance and here what you're showing. So as a result, due to the setback distance between 0 and increases, when setback distance increases for the same angle beta, your n gamma q will increase. So this was for the this was the first case was for when you have b by b equal to 0, 0.5, and this case is when b by b equal to 1 and 2. Okay. So these are the list of references which we have used in this presentation. First reference is a book by Professor Vijay Das in USA, and the title is Cello Foundations Bearing Capacity Experiment. And this is a very good book on slope stability. Then what you have the jumper line, which was used centrifugal modeling and test for cello foundation. It is a paper in Cosmo PSC. Then Graham et al. You have this in 1988. So he worked on stress characteristics also for cello footings. Then you have Hansen and Veshik, which we have discussed. Merov one is the first one who have decided, and Sarad, Sood, and Handa also work in this area. So I thank you very much for your kind attention.